Good morning. Today we are going to see about Carey Foster Bridge. Carey Foster Bridge is an instrument for precise resistance measurement. This is an instrument. Carey Foster Bridge was discovered by George Carey Foster, who lived in the year of 1835 to 1919, and he was a chemist and physicist known for application and modification of the Wheatstone's bridge for precise electrical measurements. The Carey Foster Bridge is named after him. It is an electrical circuit that can be used to measure very small resistances. It works on the principle of Wheatstone's bridge. It consists of 4 resistances P, Q, R and S that are connected to each other as shown in the figure. In this circuit, G is the galvanometer and E is an accumulator and K1, K are the 2 keys. If the values of these resistances are adjusted so that no current flows through the galvanometer, and if any of these 3 resistances are known, the unknown resistance can be determined using this formula: P by Q is equal to R by S. This is an experimental setup for the Carey Foster Bridge. It is a form of Wheatstone's bridge. It consists of a uniform wire AB of length 1 meter, which is stretched on a wooden board. 2 equal resistances P and Q are connected in gap 2 and 3. The unknown resistance R is connected in gap 1. The standard resistance S of the same order of the resistance R is connected in gap 4. A Lagrange cell is connected across M and N. A galvanometer G is connected between the terminal C and the sliding contact maker D. The contact maker is moved until the bridge is balanced. Let L1 be the balancing length as measured from the end A. Let alpha and beta be the end resistances at A and B. Let rho be the resistance per meter length of the wire. From the principle of Wheatstone's bridge, P by Q is equal to R by S. Now, let alpha and beta are the end resistances. Therefore, here the end resistances. Therefore, P by Q is equal to R plus alpha, which is the end resistance here, and L1 rho be the resistance. In this terminal, let beta be the end resistance, and here the balancing length is 100 minus L2. Therefore, if this is multiplied by rho, we get the resistance. To eliminate these end resistances alpha and beta, we can interchange this R and S, and again the bridge is balanced. The balancing length L2 is determined from this end A. Then P by Q is equal to, if we interchanged here, yes, this end becomes S and this end becomes R. Therefore, this S plus alpha plus the balancing length is L2 rho divided by R plus beta plus 100 minus L2 into rho. This is equation 2. These two are the equivalent Wheatstone's bridge circuit. That is, here P, Q, this end R, alpha end resistance, rho L1 be the resistance. This is S. Here the end resistance is beta. Here the resistance is rho into 100 minus L1. If these two are interchanged means here S, here R, but the end resistance here is alpha and the balancing length here is L2. Therefore, the resistance is rho into L2. Similarly, here rho into 100 minus L2. From equations 1 and 2, adding 1 to both sides, adding 1 on both sides. If we add 1 here, this is plus 1, here also 1 plus, and if we are taking LCM, this side means S plus beta plus 100 minus L1 into rho. This is multiplied here. We are getting this R rho L1 rho, and if we are multiplied by this one means S beta, this 100, this can be written as 100 rho minus L1 into rho. Similarly, here also we are taking the LCM R plus beta plus 100 minus L2 into rho. Therefore, this S alpha L2 rho. This one is here we are taking LCM means you multiplied this by this term. Therefore, R beta. This can also be written as 100 rho minus L2 into rho. Simplifying this, that is minus L1 rho plus L1 plus L2 rho minus L2 rho. We are getting R alpha S beta 100 rho. Here also R S alpha beta 100 rho. Here these two terms, the numerators here are equal. Therefore, the denominators must be equal. Therefore, S plus beta plus, this can be again multiplied. If you are getting 100 rho minus L1 rho, and this time R plus beta plus, if you are multiplied by 100 rho minus L2 rho. Here 100 rho we are cancel beta beta. So here S minus L1 rho equal to R minus L2 rho. So keeping R this side, we are bringing this L2 this side means we are getting here S minus L1 rho plus L2 rho. Therefore, S minus, taking rho outside, for this plus term L2 minus this term is L1. This is L1. For S plus rho into L2 minus L1. Next, we are going to find a rho, that is the resistance per unit length of the wire. Here, a standard resistance 0.1 ohm is connected in gap 1. Here, a thick copper strip is connected. Here, a thick copper strip is connected in gap 4. Therefore, R is equal to 0.1 ohm. If you are connected by thick copper strip, means here this end, the resistance S is equal to 0. Now the balancing length L1 dash is determined. Now the standard resistance and this copper strips are interchanged. The balancing length L2 dash is determined. We know that this equation R is equal to S plus rho into L2 minus L1. We know that R is equal to 0.1 S plus rho. Now the balancing length is L2 dash minus L1 dash. Here we connect this by a copper strip, therefore S is equal to 0. If we put S is equal to 0 here, then rho is equal to 0.1 by L2 dash minus L1 dash. Thus, by knowing the values of S and rho, the unknown resistance R is calculated. Next, the determination of resistivity of the wire. First, what is the resistivity? Resistivity of the material is defined as the resistance offered to current flow by a conductor of unit length having unit area of cross section. Its unit is ohm meter. To determine the resistivity of the material using this Carey Foster Bridge, the resistance R of a given wire is determined using Carey Foster Bridge. The length of the wire, here the length of the wire is measured. Same, the radius of the wire is also found with the screw gauge. Then the resistivity of the material of the wire is calculated using the formula area of cross section into resistance offered by length of the material. Therefore, R is the resistance. Therefore, R. The radius is, mean radius is R. Therefore, the area is pi R squared. The mean length of the wire is L. Therefore, we substitute L. From this, the resistivity of the material of the wire is found. The unit is ohm meter. Next, determination of the temperature coefficients of resistance. The temperature coefficient of resistance is defined as the increase of resistance per unit original resistance per degree rise of temperature. Let R0 and RT be the resistance of a wire at temperature 0 degree and T degree centigrade. Then we know that RT is equal to R0 into 1 plus alpha T. From this, we have to determine alpha, that is we are multiplied this with R0 plus R0 into alpha T. Take this R0 this side, we are getting RT minus R0, that is equal to R0 into alpha T. From this, alpha is equal to RT minus R0 divided by R0 T. This RT minus R0 is nothing but the difference in resistance. Therefore, it is represented by dr, and this T is dt, where alpha is the temperature coefficient of the resistance of the material. It is determined using this experiment. The given wire is wound non-inductively in the form of a double spiral on this glass tube. It is immersed in a beaker containing, this is immersed in a beaker containing ice at 0 degree centigrade. The resistance of the wire is determined. Now, the coil is removed and is kept at a water bath and it is heated. Now the resistance of the wire is determined at various temperatures from 30 degree to 100 degree centigrade in steps of 10 degree. Now a graph is drawn with temperature along the x-axis and resistance along the y-axis. A straight line is obtained. The slope of the line gives tan theta is equal to this dr by dt. The y-intercept, this axis is y-axis, the y-intercept here is equal to r0. From this, alpha is calculated using the formula 1 by r0 dr by deta. This r0 is the y-intercept, this dr by dt is the slope. To determine or to measure the resistance at two different temperatures, let R1 and R2 be the resistances corresponding to temperatures T1 and T2. Using this equation, RT is equal to R0 into 1 plus alpha T. We can write R1, that is resistance at a temperature T1, and here R2 is the resistance at a temperature T2. Therefore, R1 is equal to R0 into 1 plus alpha T1. Here R2 is equal to R0 into 1 plus alpha T2. Now divide one by the other, and here R2 divided by R1 is equal to R0 into 1 plus alpha T2 divided by R0 into 1 plus alpha T1. Here R0 gets cancelled. Therefore, R2 by R1 is equal to 1 plus alpha T2 by 1 plus alpha T1. Now, cross multiplied this, we get R2 into 1 plus alpha T1, that is equal to R1 into 1 plus alpha T2. Now, this can be written as R2 plus R2 alpha T2 is equal to R1 plus R1 alpha T2. Here it is alpha T1. So bring this R1 here, R2 minus R1 is equal to this to this side, R1 alpha T2 minus R2 alpha T1. Now, from this side, taking alpha outside, we are getting alpha into T2 R1 minus T1 R2. Hence, temperature coefficient of resistance is given by alpha is equal to R2 minus R1 divided by T2 R1 minus T1 R2. Advantages of the Carey Foster Bridge. It gives an accurate measurement of the difference between the resistance. Only one unknown resistance is sufficient to measure the difference between the resistance. Need less maintenance and operating cost. Less chance of human errors. It is not a very complex construction. It is easy to construct. Some of the disadvantages of the Carey Foster Bridge. The slide wire or jockey needs calibration after regular use. It should be calibrated to avoid any errors. Need replacement of electric components after a time, because with the time some characteristics properties of sensitive parts of the components like resistance and galvanometer are not the same. No scope for digital measurements. Applications of Carey Foster Bridge. The sum of the applications are: it is used to measure the difference between the resistance. It can be used to find the specific resistance of the wire. It is used to compare the two equal resistances. It is used to measure the unknown resistance, and it is also used to find the temperature coefficient of the resistance.